Welcome to our discussion on logarithmic scales, where we're going to look at some of the specific applications of them, like in earthquakes, sounds, and acids. So the distribution of earthquakes around the world, you can see, are predominantly around the Pacific Ocean. That's why this is called the Pacific Ring of Fire, because of all of the volcanoes and earthquake activity that happens from those tectonic plates um, smashing into each other or sliding against each other or actually even spreading away from each other. So the magnitude scale for earthquakes is defined so that each magnitude represents about 32 times as much energy as the prior magnitude. So the magnitude we'll define as capital N is related to the released energy, capital E, by the following equivalent formulas. So log base 10, or just log, of E is equal to 4.4 plus 1.5 times N. Or if we solve for E, we get that the energy is 2.5 times 10 to the fourth times 10 to the 1.5 M. The energy is measured in joules, and magnitudes have no units. So most people are like, what the hell are joules? Well, it's just a unit of measure for energy, similar to watts, those kind of things. So using the formula for earthquake magnitudes, calculate precisely how much more energy is released for each one magnitude on the earthquake scale. Also find the energy change for a 0.5 change. Okay, so if we look at the formula and we just plug in some numbers, the first term, 2.5 times 10 to the fourth, is a constant number. That is the same no matter what value we use for m. So the magnitude appears only in the second term, which is 10 to the 1.5 m. Each time we raise the magnitude by 1, such as going from 5 to 6, or from 7 to 8, the total energy E increases by a factor of 10 to the 1.5, because it's 10.1.5 times 1 versus 10 to the 1.5 times 2. So each successive magnitude represents 10 to the 1.5, or 31.623, as we said before, roughly 32 times as much energy. Now the change in magnitude to a 0.5 roughly gets us 10 to the 0.75, or 5.6 times in energy. So to put this into perspective, in '89, the San Francisco earthquake, in which 90 people were killed, had a magnitude of 7.1. We can calculate the energy released in joules and compare the energy of this earthquake to that of the 2010 earthquake in Haiti, which had a magnitude of 7 and killed an estimated 316,000 people. So the energy released by the San Francisco earthquake is 1.1 times 10 to the 15 joules, by just plugging in a magnitude of 7.1 into this formula and doing some math. So the San Francisco earthquake was 0.1 magnitude greater than the Haiti earthquake. It therefore released 1.4 times as much energy. Nevertheless, the Haiti earthquake killed many more people, mainly because of the lower quality in building construction and lack of resources and all that kind of stuff, right? I mean, San Francisco knows that earthquakes are coming, so they have building codes that make them build things to withstand earthquakes, where in Haiti they don't have those same rules. Now, if we want to measure decibels or sound, we put it on the decibel scale, and it's used to compare the loudness of sounds. The loudness of a sound in decibels is defined by the following equivalent formulas. So the loudness in decibels is equal to 10 log 10, again, this is just 10 log, intensity of sound over the intensity of the softest audible sound, or the intensity of the sound over the intensity of the softest audible sound is equal to 10 raised to the power of the decibel reading over 10. So here are some common sounds and their decimals. Decibels, 140 decibels, or 10 to the 14th times as loud as the softest audible sound, is a jet at 30 meters away. An inaudible sound comes out at -10. The softest audible sound comes at 1. The reason why they say the softest audible sound is you can have different scales for different things. So this is the scale for humans. So this is the softest sound that the average human ear, right? Obviously some people hear better than others, but this is the softest sound that the average humans can hear. You could also have a different decibel scale for, bats, dogs, and other creatures that hear, with different proficiencies. So the rustling of leaves, right, is 10 decibels or 10 times as loud. A whisper is 20 decibels or 100 times as loud, right? So a whisper is supposedly 100 times louder than the softest thing you could hear. And it just goes up from there, right? Busy traffic. The threshold of pain for the human ear is 90 decibels, right? So a siren at 30 meters away, that hurts. 120 decibels has a strong risk of damage. And so a jet engine at 30 meters away will definitely damage your ear, which is why people working at the airports always have those big, huge ear protectors on. Okay, how can we compute some decimals? Well, suppose a sound is 100 times as intense as the softest audible sound. What is its loudness in decibels? Well, we already saw that if it's 100 times as much, it's a whisper, and it's 10 to the 2, so it's going to be a decibel of 20. But how could we do that with the math if we didn't have that little table? Well, the loudness in decibels is just 10 log 10 of the 100 being how many times, louder it is, which becomes 10 times 2, which becomes 20 decibels. How does the intensity of a 57 decibel sound compare to that of a 23 decibel sound? So now we have to use the other formula where it's intensity of a sound over the other sound equals 10 to this stuff, right? The loudness of sound 1 minus the loudness of sound 2 all over 10. So we plug all of our numbers in and we put in the 57 and the 23 for the 2 decibels. And we get that difference over 10, which is 34 over 10, which is 3.4. And we get 10 to the 3.4, and we get that this ratio is 2512. So the sound, something that has a decibel reading of 57 decibels, is about 2,500 times as intense as a sound of 23 decibels. So if we go back to our scale, 20, a whisper, 57, ordinary conversation. So they're saying ordinary conversation is roughly, right, 2,500 times as intense. How about the inverse square log for sound? The intensity of sound decreases with the square of the distance from the source. That makes sense, right? As things go further away from us, we can't hear them as well. So that means that the intensity is proportional to 1 over the distance squared. Thus, that gives us the following, an inverse square law with distance. So how many times greater is the intensity of a sound from a concert speaker at a distance of 10 meters than the intensity at a distance of 80 meters? Well, the sound intensity at 10 meters is 64 times the sound intensity at 80 because of the difference in distance. How far should you be from a jet to avoid a strong risk of damage, right? Well, we know that the sound from a jet at a distance of 30 meters still gives us 140 decibels, and 120 decibels is the level of sound that poses a strong risk to the ear. So the ratio of the intensity of these two things, right, 140 over 120 is 10 to the 140 over 10 to the 120 over 10, basically comes 10 squared or 100. So the sound of a jet at 30 meters is 100 times as intense as a sound that represents a strong risk of ear damage. So to prevent this, you must be far enough away to weaken this sound intensity by a factor of 100. And remember, it gets weakened by a 1 over d squared. So basically, you just need the distance to be 10 because 10 squared would be 100. So 1 over 100 times 100, those would wipe each other out. So therefore, you just need to be 10 meters further away or 10 times, right? And then so you'd be 300 meters from the jet. The pH scale is another way to classify substances as either neutral, acidic, or basic. And the pH scale is also something that uses logs. So your pH is equal to the negative log of H plus, where H plus is the hydrogen ion concentration in moles per liter. Again, a lot of gobbledygook. It just means moles per liter, or moles is a unit of measure. Liter, of course, is a unit of measure. So pure water is neutral and it has a pH of 7. Acids have a pH lower than 7 and bases have a pH higher than 7. So here are some typical pHs, right? So here's your pure water at 7, baking soda, right, 8.4, household ammonia, ammonia is actually a base at 10, and then drain opener also 10 to 12. Then we look at some acids. Drinking water is actually a little acidic, slightly, right, but not enough to make a difference. Vinegar, very acidic, down at 3, right? Stomach acid, even worse, 2 to 3, and then lemon juice at 2. And then, of course, things go, even worse than that. So what is the pH of a solution with a hydrogen ion concentration of 10 to the negative 12? So you just plug these things in. So you just put in 10 to the negative 12 in for H plus, and you just take negative log base 10 of 10 to the negative 12, and the log base 10 of 10 to a power, you end up just getting the power, so you get negative 12, and you just get 12. So it's a pH of 12. And because that's well above 7, we know that that's a strong base. Okay, so I know a lot of these formulas seem tricky. What I would say is just, write them down in your notes, have them ready to go, and just realize that it's just a matter of plugging in some numbers and spitting out some answers.